In this video, we'll be looking at differentiation. Differentiation is a branch of calculus which was actually developed by Isaac Newton. We'll move on to the next example. Example 4. Example 4. We're asked to find the y dx if y is equals to 6x. So comparing it with the general form, we have that our a is 6. A is equals to 6. But what about our n? There's no number here. What is going to be our n? Now, y equals to 6x is the same thing as y equals to 6x raised to power 1. It's just because x is raised to power 1, that is why it is not written. It is assumed anywhere in the world that there is an invisible 1 there. So it is not written. But when differentiating and there is nothing written, the x is not raised to anything. So know that x is raised to power 1. So just like before, our dy dx is going to be, based on this formula, that will be 1 times 6 x raised to power 1 minus 1. So from here, 1 times 6 is 6. 1 minus 1 is what? 1 minus 1 is 0. So our answer is 6x raised to power 0. But we're not going to leave it this way. From your previous work, if you've done indices before, indices says that when a number or an alphabet, anything that is raised to power 0, that thing becomes 1. So x raised to power 0 is the same thing as 1 is equals to 1. So we're going to have 6 times x raised to power 0 is 1. So 6 times 1 is equals to 6. So the x is actually equals to 6. The y dx is 6. So x raised to power 0 from indices, anything raised to power 0 is equals to 1. So in place of x raised to power 0, we put 1 there. We now multiply by the constant 6, which was already there. 6 times 1 gives us 6. So our dy dx, when y is equals to 6x, is equals to 6. Okay. Now, based on this current example, how about, let's assume if you're doing, when they said we should find the y dx if y is equals to 6x, and at the end of the day we discovered that our dy dx was equals to 6. So how about if you were asked to find the y dx if you are asked to find the y dx if y is equals to 2x, what is going to be the y dx? If you look at this, just compare them. When you analyze, the answer are going to be similar. Here, y was equals to 6x, the y dx was equals to 6. Why? Because the x at the end of the day was raised to power 0, which disappeared. So in this case now, where y is equals to 2x, if you solve, you will discover that the y dx is equals to 2. The y dx is equals to 2. Just try it and see. Using the procedure, using the formula, the y dx will be 2. Also, if you were asked to find the y dx if y is equals to 100x, by comparison, when you solve, you will discover that the y dx is equals to 100. So whenever you have a constant with a variable that is raised to power 1, that variable will disappear and the y dx will just be equal to the constant. Okay. Example 5, we're asked to find the y dx if y is equals to 100. Now looking at this, y is equals to 100. If you compare it to the general form, you observe that there is no x. There is a is 100. But x does not exist and n does not exist as well. So how are you going to apply this formula? So what you're going to do is that you will introduce x from indices. So let's modify y is equals to 100 as 100 times 1. 100 times 1 is the same thing as 100. So we are going to introduce x in place of the 1. When you raise x to power 0, x raised to power 0 is what? Is actually equals to 1. Now, we are giving y is equals to 100 and we now modify it to 100 times 1. Actually, we will not alter anything because 100 times 1 is still 100. Now, in place of this one, we put x raised to power 0. So we're going to have 100 times x raised to power 0, which at the end of the day, 100 times x raised to power 0 gives us 100 x raised to power 0. So y equals to 100 can actually be rewritten as 100 x raised to power 0. So we've successfully introduced x. We've not changed anything because x raised to power 0 is 1 and 1 times 100 is 100. Okay, I hope you observe. So now we're going to proceed to differentiate 100 x raised to power 0. So y is equals to 100 is the same thing as 100 x raised to power 0. So right now our a is 100, our x is x, our n is 0 and our y is y. So applying the formula, the y, the x is going to be equals to n times a, that's 0 times 100. So then x raised to power n minus 1, our n is what? 0. That is going to be 0 minus 1. What is 0 times 100? 0 times 100 is 0. 0 minus 1, it's minus 1. Now anything multiplied by 0 is 0. So 0 times x minus 1 is going to give you 0. So the y dx is equals to what? 0. The y dx is equals to what? 0. So this was a special case of differentiation. We're giving y is equals to 100. There was no variable, there was no x, although we introduced it to be able to use the general formula to solve. But we're giving 100 is equals to x, that is a constant. Now, whenever in differentiation you're giving anything to differentiate, and that is just a pure number, there's no variable, there's no alphabet. When you're giving, if any number, any constant to differentiate, your dy dx, your gradient function is going to be equal to 0. Take note of that. So I'm going to show you. For instance, if you are given y is equal to 6 to differentiate, to find the y dx, your dy the x is going to be equals to 0. if you are given y is equals to minus 6, your dy dx is going to be equals to 0. Let me prove this one using the general formula. Okay. Like I said, if y is equals to 6, if you want to introduce x, you're going to attach x raised to power 0 to the 6. X raised to power 0, like I told you before, is 1. And 1 times 6 is actually still 6. So you've not done anything wrong. You've not increased the number. You've not decreased it. This number and this one are still the same thing. Okay. So now your dy dx is going to be equals to 0 times 6. Based on this formula, then x is going to be 0 minus 1. 0 times 6 is what? 0. And 0 times x raised to power 0 minus 1. X times 0 is still 0. So your answer is 0. The y dx is equal to 0. So for any constant function, when you're given a constant, when you're given a pure number to differentiate, your dy dx, your graded function is equals to 0. So if you're having any issues, just go over the video. Go over it over and over till you master the techniques. So we've come to the end of differentiation using the general formula.